All right, and it's 5:25, time for our next session with Brian Korzynski. Brian's going to be talking to us about what does it mean to be a data scientist, and he's going to essentially sift through all the misconceptions and discuss his own experiences in real life. Brian's a senior machine learning engineer at Iron Mountain. He had an extensive career in Microsoft Technologies, working for a variety of companies, both large and small, working in a variety of different industries. And he's been an avid developer as well as a speaker at a variety of different conferences. Currently, he's working on a variety of machine learning and artificial intelligence applications to aid in the applications that he's working on at work. And so with that, I will turn it over to Brian.
Thank you, Sam. So before we begin, one of the things I do want to mention is I have the chat window open on another window. So if you see me kind of looking off to the side, I'm kind of looking at the chat window to see if you have questions. If you have any questions as we're going along through the process or at the end, please feel free to post it in there and I'll stop and address those as they come up. So a little bit about me. So I'm from Michigan. So as Sam and I were just talking, I can do the hand thing. I'm about 30 minutes north of Detroit, about right here on the thumb. And one of the things I wanted to talk a bit about is not necessarily to convey my resume, if you will, but I wanted to show that I've worked in a variety of different machine learning positions, from being a data scientist to being a machine learning engineer, and most recently being a machine learning architect. And I want to explain what some of the differences between these things are, and hopefully that will better convey what these concepts are so that you're not so confused. I've been a professional developer now for almost 13 years, not quite 13 yet. I've done a variety of apps, Windows Forms, web, mobile, SQL optimization, and most recently has been cloud and machine learning. So before we get into talking about like what a data scientist and stuff is, I need to make sure that we have a basis of knowledge. So I want to take a step back and I want to talk a bit about some of the terms that you'll see centered around data science, machine learning, artificial intelligence, because a lot of these terms get thrown out there, but I don't think a lot of people actually understand what they mean. And I think they kind of get confused or use them interchangeably. So I wanted to kind of convey what that means. So I kind of want you to think of this as like an onion. So we have on the outermost layer is artificial intelligence. Artificial intelligence is development of tasks that usually require human intelligence, things such as like facial recognition or searching. And the way I want you to think about this is artificial intelligence is a set of algorithms for coding things that are easier for humans to do, but hard to code, okay? Machine learning is a subset of artificial intelligence. It uses algorithms and models to perform tasks without explicitly being told the instructions and relying instead on patterns and inference. So the way I want you to kind of think about machine learning is think of it as a rules engine where it figures out the rules based upon samples that you give it. So you're not actually specifying the rules for the rules engine. You're letting the machine figure out those rules based upon those patterns and inference that it determines. And within machine learning is a subset known as deep learning. So deep learning is a set of methods that uses something called artificial neural networks, or just neural networks for short. And those are a set of algorithms and techniques that apply the machine learning principles, but at a deeper level. And we'll look at an example of what a neural network looks like here in just a few minutes. But I wanted to point that out because machine learning is artificial intelligence. Deep learning is machine learning, but artificial intelligence does not necessarily imply machine learning nor deep learning, okay? So there are some things in artificial intelligence, such as searching, that are not specifically machine learning problems. Okay, so I wanted to kind of convey that point. And the next thing we'll look at is the types of problems you can solve with machine learning. So machine learning is basically broken down into 4 different types of machine learning. The first of these is supervised. Supervised meaning I'm going to give you data, and I'm going to give you sample, or I'm going to tell you what that data represents, right? So I'm going to give you samples of email, and I'm going to tell you which ones are spam and which ones are not spam. So if I'm giving you the label, meaning the classification, like is it spam or is it ham, or what type of document is this, or is this part defective, whether it's that's called anomaly detection. If I'm trying to predict a label for something, this is what's known as a classification problem. If I'm trying to actually predict a value, such as, given past sales history, what is our sales likely to be this month? Those types of things are called regressions because we're trying to predict the actual values. This would be things like trying to predict weather, trying to predict sales, trying to predict, those types of things. Unsupervised learning is where you're giving it the data, but you're not giving it any other information about the data. And you're trying to discover things within the data. So one of the things that you can utilize is something called clustering. And it says, which of these data points are most alike? So if I have a set of documents, I can kind of group documents together and say, which of the, like there's this cluster, these things are all have, similar characteristics or similar traits. So based upon that, I can actually use that data to actually help build my supervised models. Another thing that you find in there is something called dimensionality reduction. And it says, which of these features are not needed? So let me give you an example of that. Let's say that we're trying to determine a bank statement, right? We're trying to build a model to determine if something is a bank statement or not a bank statement. Well, there's things that you might have on a bank statement, such as a balance, like how much money is left in their account. Well, that's a data point we could extract, but we don't really want that in our model, right? So based upon dimensionality reduction and an analysis that we can do with that, we can determine that this data point that we've captured, we don't actually want to use in our supervised learning to build classifiers. Okay, so dimensionality reduction is all about reducing the amount of features that go into a model, and we'll look at what features mean in just a few minutes. Okay. Excuse me. So next is recommendation engines. And I'm sure everybody's familiar with these. If you've used Amazon or Netflix, if you've bought this or you watched this, then you might also like this other thing. So that one's pretty self-explanatory. And the last one is reinforcement learning. This is a risk-reward system, similar to how like we as humans learn. And this you've probably heard of from like self-driving cars. This is like a very, very advanced form of machine learning that basically uses techniques taken from supervised and unsupervised, as well as building other metrics and stuff around it, and then using that to build out applications that do really complex things. Okay, so these are the types of problems you can solve with machine learning. So let's talk about some other concepts you hear around data science. And one of those is data lake. So I'm from Michigan. So this is a picture of a Great Lake, all puns intended. And as you can see, basically what it is just a container that holds files. It could be Word docs, it could be videos, it could be PDFs, it could be Excel files, it could be PNGs, PDFs, JPEGs, whatever. The file type doesn't really matter. So it's contrary. It's different than like a normal database, where if you think about a database has to have a defined structure. The amount of data you put into that row has to be a certain size. Where this PDF file here, it could be 10 gigs, and this Word doc could be 10 meg, right? So there's no size limitations or anything like that. It's meant as a container to hold your data. So with this, I actually like Amazon Web Services definition, and it says a data lake is a centralized repository that allows you to store all of your structured and unstructured data at any scale. So data lake, for example, is one of those things that they try to make sound really complicated. But if you're already using cloud platforms such as S3 or blob storage, then you're already using basically a data lake anyways, right? Because in AWS, a data lake is nothing but a combination of S3 and Glacier storage. Glacier for long-term storage that maybe once you're done processing data, you don't need it in the lake for current processing. Azure Data Lake is actually built upon blob storage. And what that does, and the differentiation between the Azure Data Lake and the blob storage itself, is that there's some abstractions around that for something called the Hadoop distributed file system. And we're not going to necessarily get into what that means, but basically we'll talk slightly about Hadoop when we get to the big data section. Yeah, so that's the difference between just straight up blob storage and the Azure Data Lake. And then there's also Google Cloud Storage if you're on the Google platform. There's also some on-premises versions of these. Most notably are MinIO and then NoSQL offerings such as Mongo or Couchbase. So that's data lake. And it looks like we still have no questions, so we'll continue on. The next big one I want to talk about is big data. And the reason why I really want to talk about big data is because a lot of people, if you're reading a lot of things online, you're going to see a lot of people try to equate big data equals data science, but that's not necessarily the same thing. And I wanted to give you kind of the definitions, and I wanted to kind of break down what data science is so that you can understand what is and what is not data science. So big data is a field that treats ways to analyze, systematically extract information from, and otherwise deal with data sets that are too large or too complex to be dealt with by traditional data processing application software. Okay, so let's actually take a more in-depth look at that. So to break down data science, or not data science, but big data, one of the things that you'll commonly see, and this is the core of big data, is something known as the 4 V's. They are volume, variety, velocity, and veracity. So the easiest one to understand is volume. So a lot of people say, well, I have a 100 terabyte database, or I have a 40 terabyte database, or I have 40 terabytes of files. And handling those files and maneuvering through them through your system creates a lot of challenges, right? When you're hitting 100 terabytes or petabytes or something like that, that's a huge problem you have to deal with. Another side is variety. Maybe you're doing some image processing, and maybe your images might come in as JPEG, PNGs. They might even come in as videos. Maybe it's a live image, from like an iPhone, where maybe you're extracting a frame out of that video. So there could be a variety of sources that your data comes from. And that variety could be a lot of sources. You could have 150 different connectors or something like that that's pulling data into your application. And that again, means that you have to handle the problem in a certain way. The other two are velocity and veracity. Velocity means you have a lot of data coming in very fast. So think of it as like a car, right? If I'm trying to build a pedestrian detection system and I have 10 cameras mounted on a car, and each of those cameras are running at 30 frames per second, that means I have 300 frames or images, if you will, coming in that I need to process every second. That's a huge amount of velocity of data coming in. And depending on what your applications are and things like that, that might either be a lot or it might not be a lot at all. And it depends on where you're doing that processing, right? So if in that example, if you're doing the processing in the car, then that becomes a huge problem that you have to deal with. If you're sending it up to the cloud or something, it's maybe not as big a deal. So there's that type of thing. And then the last one is veracity. Veracity is uncertainty of the data. Let's say that I have a mortgage system where I'm allowing borrowers to upload their own tax documents and things like that. I might not guarantee that they know what they're uploading, or they might label something wrong or whatever. So there's a certain amount of uncertainty with the data that needs to be verified. Okay, so this is what big data is. And I wanted to point this out so you have like a frame of understanding of what big data actually is. Okay, so any questions about that? Okay, good. So now what I want to do is I want to get into a kind of like a hello world machine learning example. And this is the data set you can find just very easily by Googling the iris data set. And what it says is that given certain features of a flower, so there's the sepal and the petal, given the length and width of each, I can properly identify which of the 3 types of iris it is. So over off to the right here, you see this is a sample of the first 5 rows taken out of the data set, and you can see the values. So what I wanted to do here is I want to give you a understanding of what machine learning process would look like, so that we can talk about the roles and stuff when we get into like what is the actual definition of data science versus data engineer versus data architect, those type of things. Okay. So we take this data. So this is the raw data that we have. And what we first have to do is we have to normalize the input. So if we look here, each of these 4 columns that are our values are considered to be equal in machine learning terms, right? So if we have values that are like 7.9 and we have values that are 0.2, the 7.9 is way going to outweigh the 0.2 value, and it's going to make our model lopsided. So what we need to do is we need to perform an analysis or a normalization process across the data so that this column is equally important as this column, is equally important as that column, is equally as important as that column. Okay? So let me talk about how we normalize that data. So the very easy way of doing it is you just look at each of the columns, you figure out the minimum and maximum value for each of those data points, and then you can run it through a range normalized value. So let's say under the sepal length, we have a value of 5.7. So we take our 5.7, we subtract off our 4.3 from it, and then divide that by the 7.9 minus the 4.3. This will give us our normalized value as a value between 0 and 100. And if we do that across each of those 4 columns, now each of those 4 columns can be directly compared against each other because now they're respective of their own ranges. Because you can see here, this range is 4.3 to 7.9. This one is 0.1 to 2.5, right? So that's the reason why you have to normalize your data. Okay, so now that we have our normalized output, we have to figure out what are our possible labels. So based upon the first slide I showed you there, we had setosa, virginica, and versicolor. Then we have to assign a label, if you will. So we're trying to predict a label, so this is classification. And we have to assign the label to each of those data points. The way we do this is a technique called one-hot encoding. And it says that you have a label or column for each of the possible labels. And then you either put a 1 or a 0 in there corresponding to whether it is that label or not. And give me 1 second and I'll show you what I mean by that. So if you look here on the top, this is our raw data that we were given again. And down here, you can see that we basically added 3 new columns, setosa, virginica, versicolor. And depending on what the label is, so you can see here, the setosa. So we put a 1 under the setosa column for each of those values and a 0 for every other label that there is. And this is kind of a bad example because what I should have done is taken 5 random rows of the data so that you'd have a variety of different labels instead of just the 1. But we'll go with that for right now. So you can see that what we have is we took each of these values. So the 5.1 became 0.22 or 22%. So these are percentages between 0 and 100 represented as decimals. So this is 22%, 17%, 11%, etc. Okay, so these 4 columns that we originally had, these are what we're going to call our features or our input. These new columns we added over here are our outputs or our labels, right? So this is what we first have to do is we have to convert those things into numbers. And now that we have numbers that are normalized, now we can actually do something with this data. Okay, any questions so far? Hopefully that's clear and easy to follow. Okay, good. So now what we can do is we can construct a network. So if you notice, I just shortened the labels to sepal length, sepal width, petal length, petal width. And what we're going to do is we know we have 4 inputs, right? 1, 2, 3, 4. So we're going to have 1, 2, 3, 4 values here. We know we have 1, 2, 3 outputs, and we're going to do 1, 2, 3 outputs here. And this is what's called a neural network. So what we're going to do, let me just go to the next image for a second, is we're going to take the values from these positions here. We're going to put them in here, and then we're going to take our outputs, put them there. And what we're going to do is we're going to construct a neural network that it's going to randomize these weights on each of these lines that you see here. And it's going to figure out a mathematical formula on how to take these inputs and turn them into these outputs across all the data rows. Okay, so I don't necessarily want to get into how do we construct the hidden layers, how many nodes. That's a little bit outside the topic of this conversation. But if you are interested in that, you can always hit me up. My details are at the end of the slide, and we could talk about that. So by doing this, by building out these numbers, this will give it, and then we let the training run. It goes all the way through, figures out an error rate says, nope, you're 50% correct. It goes back and updates all these weights, and then it tries it again. It goes back and forth and back and forth and back and forth. That back and forth, so all the way through and then all the way back, is called an epoch. So when it's training, it goes through several epochs to actually train the model. So hold on, let's see if we have a question. Oh, you're talking about these values here?
Yeah. You said they were like 22%, and I wasn't sure of what.
Yeah. So if we go back to the normalization really quick, let me just show you this. We know that that was 5.1, right? So we know that 5.1 is a number between 4.3 and 7.9, right?
Mm-hmm.
So this is effectively our 0. This is effectively our 100, right? So think of it as like a range. So how far into that range is that percentage? So that 22% represents that slider has moved up to 22% of that range. So even having that 22% and knowing these two values here, we can actually convert it back to get back that 5.1. You can actually take the inverse of this formula. Does that make sense?
Yes, thank you.
Okay, cool. Sorry, I should have done a better job explaining that. But anyway, so we build the network, and now we have a model that will, given these inputs, it will actually make these predictions and give us back the values. So now that we've talked about a simple machine learning example, one of the things I want to talk about is data science, and then I want to get into the roles of data science, and then that'll come back full circle to the models that we just built. Okay, so the first question is, what is data science? So the simple answer is everybody has their own definition. There's not really an official one, and it can vary from company to company and how people view it and whatever. If you do some Google searching, you'll probably find diagrams like this. And I kind of like this because it gives you a good general idea. But just like with anything, you have to take it with a grain of salt because it's not an absolute, right? To follow this says that data science is the intersection between computer science, math, business knowledge, traditional research, software development, and machine learning. Well, maybe a data scientist doesn't do traditional research, or maybe they're not great in software development. So you can't take it as an absolute. And the other thing too is it's kind of coming from your perspective of how you read this, because if you are a data scientist, then you're going to read this in one way, versus if you're a programmer, you might read it in a completely different way, right? So I think that a lot of these things help to kind of give you a general idea, but at the same time have to be taken with a grain of salt because it's not a true picture of what a data scientist position will be, okay? So if we take a look at the Wikipedia definition of data scientist or data science, it says data science is a multidisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from structured and unstructured data. So I kind of like this definition, but let's break it down a little bit. So data science is a multidisciplinary field, meaning math, programming, machine learning, that uses scientific methods, processes, algorithms, and systems. Basically, we use the scientific method, right, that we learned back in middle school, high school. We state a purpose, we perform some research, form a hypothesis, conduct an experiment, analyze the results, form a conclusion, lather, rinse, repeat, right? To extract knowledge and insights, so basically we'd have like a PDF, and we're trying to turn that into like tabular data that we can actually feed into our business systems to actually do something with it from both structured and unstructured data. This is one of the things that people get confused on a lot between what structured is and what unstructured is. Structured data is what you as a programmer are already used to seeing. This is data in a database. You have like tables and rows and schemas. It would be data like in a CRM, ERP, those type of things. Unstructured data are files, essentially. They might be text files, audio files, videos. They could even be like XML and JSON, where you have to take those from different sources and convert them into a format that you have to then use. But that's kind of a gray area with that, whether that's data science. So even if you just did some conversion from XML to that, that a lot of that typically falls more under programming than it does machine learning. And the other thing I wanted to point out about the Wikipedia definition is if I was to replace the word data science with machine learning, that same statement still holds true. Machine learning is a multidisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from structured and unstructured data, right? So this kind of helps to give us a basis for what data science is, but it doesn't differentiate between what is data science and what is machine learning. Okay, so we are going to hopefully answer that when we start talking about roles here. But before we do that, I wanted to talk about a traditional ML process. So the boxes in blue are what I would call programming problems or programming concerns, and the ones in green are machine learning concerns. These are ones that require special knowledge and special techniques and tools and stuff like that to actually perform them. But basically, it starts by defining a process. Then we have to collect some data. We have to clean and normalize that data. We have to split it into training and testing sets. And the reason why we do that is because we don't want to give it all the data, because if we give it all the data to build a model, then we have no way to validate that the model works correctly without getting more data. So that's why we perform that. Then we develop a model. We would train the model using that training set, evaluate the model using the testing set, publish the model, monitor, and then updating. So I kind of want to break out the roles of who will be doing what in a traditional AI organization, and that will kind of help to solidify more of the understanding of what a data scientist actually is and what they actually do. Another thing that I wanted to point out here is this is more of a component diagram of a typical machine learning project, and this is basically at a bare minimum. So at a bare minimum, you're going to have some kind of storage, whether it's a data lake, a folder, a database, whatever. You're going to have several different data sets, whether it's training, testing, validation. Validation is not necessarily required, but it's basically the same as a testing set, where we just have basically it's more data for a testing set, essentially. And the main differences is the testing set is used to evaluate the model, where the validation set may or may not be. Okay, we'd have one-to-many models here, depending on what type of application we're building. And then we have different sections within the project of how this actually works. So we have the share components, and these three share components here, the feature extractor, the normalizer, and the vectorizer, are actually used by the training process, the testing process, and the prediction process. So let me explain what these kind of are. So the feature extractor would be how we would pull features from the data that we have. Like how do we get, basically how do we turn like a PDF file into numbers that we can utilize? Okay. Then it would get passed into the normalizer, which would normalize the values like we saw with the iris data set, where we get those so that each column or each feature in that set is considered, equally important as every other feature. And then we actually have to convert that into numbers. Okay, or convert it into vectors rather, or tensors that we can then utilize. So these three things happen at the beginning of each of these phases, right? And the reason why is because we have to make sure that the same process we use to convert a PDF file into numbers is the same when we train the model as it is when we go to do prediction. Because if they're not the same, then your model that you trained is going to be of no use to you in prediction time. Okay? So then it would call the trainer. The trainer would actually, train the model by retrieving data. So it'd call into the data retriever, retrieve data, train the model. We'd apply any problem-specific logic we have. And then we're all said and done, we would serialize the model so that we can actually, save it and then recall it later on. So then when we go to do testing or prediction, if you look, these two are exactly the same thing. The only difference between these is the tester will actually evaluate the metrics, right? So like, for example, let's say we have 1,000 items in our collection and we take 200 and put them in our testing set. The tester will say, okay, so I validated the model against these 200 samples. How many of those 200 samples did you get correct? And then that metric will be how we determine, things like our precision, our recall, and some of the other metrics that we care about. And then outside of that, we also have, web services, reporting, and then basically a database of prediction data. So this is something I highly recommend if you're going to do machine learning, is you have some way to actually store the results going, or the requests coming through the system, so that you can actually evaluate your models, not from just a recognition rate perspective, but how it's actually performing in production. Okay, then external apps. So I know this is a lot, and I wanted to break it down because when a lot of people start with machine learning and just look at machine learning in general, they think it's just, you know, I have some data and I train a model, and they think it stops there. But the fact is in order for the project to be successful, you have to have all these components at a minimum, and you may even more depending on how many machine learning models you're using in your system, depending on how many different types of problems you're solving, etc. Any questions about that before we move on? Okay, cool. So now let's talk about roles in a data science team and machine learning team. So I'm going to pose a question. What's the difference between a programmer, a software engineer, and an architect? Does anybody want to venture a guess? We'll give it a minute, see. Okay, yep, architect is definitely worried about the structure. Yeah, how about the other two? Are they the same?
No, I would say the programmer is more like the worker bee.
Yep, okay, I could agree with that. And I think the answer is, it all depends on the company. I've worked at companies in the past where these three things all do the same exact job. It's just more or less, you get a different title depending on what your level of expertise and your skill level is, right? But the truth is these three things do have actual definitions, right? A programmer is someone who writes code. Anybody could be a programmer. Software engineer is basically a higher level programmer that applies engineering principles to the design, development, maintenance, testing, evaluation. It's basically, the way I look at it is basically it's a programmer that has more experience and cares more about certain things around the code that they're writing, not just, you know, writing some code. Okay, so that's one of the ways that I look at that. And as Sarah alluded to, the architect is someone who deals with the high-level design of how systems come together and choose the best technologies, handle mappings between business requirements and engineering requirements, and those type of things. So programmers and software engineers are more hands-on, actually doing the code to actually get it into production. A software architect is more or less making sure that everything comes together, that follows the plan, and all the systems communicate and talk together. So like I said, companies tend to use these interchangeably to denote a person's rank or skill level, especially if there's a lot of overlap in the responsibilities. So here's a little bit harder one. How about programmer versus computer scientist? Does anybody want to venture a guess on that?
I would say the computer scientist comes up with algorithms on how to, let's say, sort a list or a table the quickest possible way, and a programmer simply implements what the computer scientist had developed.
Exactly. So yeah, so the reason why I bring this up too is a lot of us have gone to school and gotten computer science degrees and now work as programmers or engineers or architects. So as Sam just alluded to, a programmer writes code to solve business problems, whereas a computer scientist develops new products to solve computing problems, choosing the correct technology, that type of thing. So what is the biggest difference between these is their focus. The programmer focuses on applicability. The computer scientist focuses on research, right? So the computer scientist is focused on, like Sam alluded to, finding the optimal solution, creating, you know, structures and data structures and algorithms around those structures to actually create tools that programmers can then use to solve business problems. But the biggest difference between them is that a programmer is focused on the applicability, and a computer scientist is focused on the research. Okay, so now let's bring that over to machine learning engineer versus data scientist. Well, a machine learning engineer, just like a software engineer, is a developer that writes code to solve business problems using machine learning. And a data scientist develops new products to solve machine learning problems, choosing the correct technology for dealing with the problem, dealing with compliance and other high-level tasks. And again, the difference is what their focus is. So machine learning engineers are focused on creating production applications that solve a problem for a customer need. They focus on the applicability. Data scientist focuses on the research and creating new structures and new techniques for how to solve problems and other things associated with that. Okay, so that's the biggest difference between a machine learning engineer and a data scientist, right? There might be a lot of overlap, just like engineer versus programmer. There might be a lot of overlap in things, and it might depend on the company you work for and that type of thing. But the biggest thing is that a true data scientist focuses on the research. All right, so now I want to talk about some other roles in data science and some of their responsibilities. Because another thing you'll find a lot is you'll find roles like data engineer, data architect, and like what's the difference between a data engineer and an ML engineer? So programmers, as we talked about, so programmers integrate machine learning applications into their services for other applications. So basically, let's say I have a machine learning service that will identify if this document is a bank statement or if it's a tax document. So the machine learning engineer would build out that application. The programmer would then use that application within another application. DevOps does what DevOps does. They deal with deployment, monitoring, infrastructure, and everything else with the application. Data engineer focuses on gathering, organizing, and preparing data for machine learning applications. This includes a process called munching and labeling. We'll talk a little bit more about what munching is when we look at the actual breakdown of the roles or the responsibilities. But I just wanted to mention that here. So the data engineer is basically doing engineering work and building applications and things like that is centered around preparing data for machine learning. The data architect works just like a software architect. They establish data security, storage, access standards so that you can determine who has access to this data, what applications are going to have access to this data, where are we going to store it, how are we going to encrypt it, all that kind of stuff. The machine learning engineer is a programmer that works closely with the other roles to create ML models and applications that use the data. Their focus is on machine learning problems, not traditional programming problems like that of the programmer. So if you think back to that diagram I had where it was like a workflow and then it had the two green boxes, those two green boxes are where the machine learning engineer spends their time. They might create programs, they might create tools, they might do whatever, but it's always in the context of those two boxes. And whereas the programmer is focused on the other boxes that are not those two boxes. Okay, hopefully that makes sense. So the data scientist performs similar function to that of the ML engineer. However, just like the computer scientist, they're focused on the research and other high-level or generic tasks. So in short, machine learning focuses on that. Yeah, so we just talked about that. So let's look at some responsibilities that go along with a machine learning process, and let's talk about who would be responsible for what. So if you're looking for different opportunities within the business for using machine learning, that would typically be the role of the data scientist because they have an in-depth knowledge of the different techniques and different types of problems they can solve and that kind of thing, so that they can help the business identify different opportunities and actually prepare that. So that kind of goes into defining the problem, same thing. Defining the metrics for success, the same thing. So that's basically figuring out what your requirements are so that if we build a machine learning model to solve a business process, how do we know that we've accomplished our goal? Okay. Then from there, you'd have to establish your data security, storage, and access standards. Again, your data architect. Choosing algorithms it would be data scientist. Deciding how much data is needed would be a combination of the data engineer and the machine learning engineer, depending on how in-depth knowledge the data engineer has. But typically those two roles really work closely together to make that determination. To discover how much variability is in the data set and how to handle the data set when there is a lot of variability. That again would be the data engineer and the data scientist. The data engineer would figure out how much variability. The data scientist would put together a plan of how to handle that variability into the model, which would then get passed down to the ML engineer. Then you collect data, label data, cleanse data, and normalize data. Those steps combined are what's called data munching. So that'd be where you take the data out of a database, you would label it correctly, you could prepare it for machine learning, you normalize the values to make each column equally weighted. So that process is what I mean when I say data munching. Then splitting the data into training and testing sets, again, data engineer. And the data engineer would even do human bias analysis. So what this would be is, let's say you're doing a facial detection algorithm. One of the things a data engineer would do would be they would figure out, do you have a representative enough data set to actually do that without it being biased? So that would mean you'd have all genders covered, you would have all races covered, and whatever other analysis that would have to be done with that. You would cover all that, and that would be the data engineer's input to help validate, to verify that. The machine learning engineer would then create models and validate those models. And then once that's all done, the models would get handed over to the programmers. Programmers would incorporate it into the application. Deployment and monitoring would be handled by DevOps. And then the final reporting of the model and how it's actually doing in production would be reported on by the data scientist. So I know that's a ton of stuff. And I want to see if there's any questions. So you said functional versus investigational. Can you elaborate a little bit on it? Oh, okay. Sorry. Okay. Sorry, I didn't see that. Okay, so that was the answer for the question earlier. Okay, so let's drill in a little bit more on what some data scientist responsibilities are. So in addition to creating, generic models and tools and stuff like that, there's also some other responsibilities that a data scientist has to work with. So one of the things is ensuring compliance standards, such as the EU General Data Protection Regulation, or GDPR for short. So what this is this is a set of standards around machine learning algorithms and things like that. In that, if you make a prediction, then you have to be able to describe how you made that prediction, which can be kind of challenging when you're talking about a black box where it's figuring out the rules. So there's that kind of thing. There's also what they call a right of refusal, and that right of refusal says, hey, so-and-so emailed us and said they do not want you using their data for analysis. So being able to pull their data out of the data set and things like that. So even though this is a European standard, this is actually something that a lot of American companies are starting to adopt because they know that coming down the line, this is something they're going to have to deal with, especially if they have international customers. So that is one of the things that a data scientist has to figure out is, okay, so now we have somebody's data in our model. How do we get it out of the model? So that's one of the things there. Normalization strategies. So as we saw earlier, it was just the range normalized, but there's like 100 different other normalization strategies, and which ones apply where and what gives the best performance for the model is kind of the purview of the data scientist. Choosing the standard platforms and tools. So that would be setting up, okay, so we're going to use Python, we're going to use TensorFlow, and so the platform would be Python, and the tooling would be TensorFlow, maybe Jupyter Notebooks, some Pandas. So they would kind of set forth that, and then they would also say, okay, we're going to use this version of it, because like in Python versus .NET, versioning and making sure that everybody's on the same version of frameworks is very important compared to what it is in like C#. So like, for example, in C# we have NuGet, right? So I can have two different applications that have two different versions of the same package. Well, you don't have that in Python, because in Python, packages are installed at the operating system level. And the way you get around that, if you're going to do that, is you'd have to create all these virtual environments and then install all your packages into that virtual environment. So ensuring that everybody's on the same platforms and same versions and same tools is actually like really important to do, especially when you're doing Python. They would actually help with tool creation. That could mean, maybe like ways of actually performing that feature extraction, or maybe some new normalization methods or whatever. They would create that kind of stuff. Help diagnose issues with the model. So let's say you have a machine learning engineer that's trying to implement a model or model strategy that a data scientist has come up with. They would actually help diagnose issues with that. And then also generic model creation and transfer learning. So we'll look at that one here in just a few minutes as well. Okay, any other questions before we move on? Cool. So hopefully that gives you a good rundown of what the roles are within machine learning and data science projects and what their associated responsibilities are typically. So with that, like I said, a lot of these, this is assuming that you work in either a company that's AI centric or you have a large amount of AI work to do, that you would have out these certain roles. So this is more or less a guide of who, like if you have these certain roles, who would actually perform what action. But in practice, it all depends on your company and how things get laid out. So for my work, it's some of the work I've done as a machine learning engineer, it was me and a coworker. So we basically had to figure out and split up tasks to who's going to do what. Who's going to find the data, who's going to prepare it for machine learning, who's going to build the models, who's going to incorporate it, who's going to build out the pipeline. So that's one of the things I wanted to point out, is because everything there is subject to change. This is more or less if you have the proper structure, these would be who does what. But if you don't, then obviously it can all fall back to you. For my work in data science, I actually had several machine learning engineers that would work under me and handle a lot of the programming stuff, and then everything else was handled by me. So they would do the work of the machine learning engineer, the data engineer, and that kind of thing. And then I would prepare, like, figure out how to build the model, the types of models we're going to build, set out the metrics, conveying that with the customer, figuring out customer metrics, and all that kind of stuff. So let's take a look at a slightly more complicated example than the one that we looked at before with the iris dataset. And let's say that we want to build a classifier that can determine if an image is of a blueberry muffin or of a chihuahua. And with this, I want to kind of lay out who would be responsible for what, or how those responsibilities that we talked about in that whole list format actually applies into a visual example. So as I alluded to, the data engineer would be the person that gathers the data, labels it, and prepares it for the model creation. The architect would be who's going to figure out where we're going to store that. The data scientist figures out things like, okay, so we have images. Well, what we see is a cat, but what the computer sees is just numbers, right? Just pixel colors, right? You see RGB values between 0 and 255, and then there's 3 of those, one for R, one for G, one for B. But machine learning algorithms only work with numbers. So one of the first things that you have to do as a data scientist is you have to figure out how to convert this image into usable numbers for your model, just like what we did with that the iris data set earlier on. Then what they would do is they would figure out a technique of how do we construct these numbers. So maybe they take an image and they're going to cut pieces of it off. So basically they put a window on it, they're going to cut a piece off, slide it over, cut a piece off, slide it over, and that's going to create these chunks of image, or basically these sub-images, as you see here, where this one little piece right here becomes the piece over here. Then they're going to basically do some math to what they call pooling, which is basically condense. Let's say you have 100 layers here. You're going to condense it down to 5 layers here. And then you're going to take pieces off of that and run it over and over again. So these 2 steps here, the convolution and pooling, will get repeated down and down and down. So it's the data scientist's responsibility to figure out how do we build machine learning models to actually handle this type of data. So let's say, for example, we're working with video. How do we handle video? Right? There's different techniques, but the most common used technique is basically you convert each frame or each video. You basically take the video, convert it into a set of frames or set of images, and then you would perform an image analysis across that. So when they're all said and done and figure out this whole process and get everything working, one of the things they can do is they can build out a generic model. So this might be a little hard to read, and that's okay, because it doesn't really matter. This is a layout, just like we saw with our neural network in the beginning. Each of these different steps that you see here are actual neural networks, and this is how they all get combined together to actually make a prediction. This is something known as a Google net, and this would be an example of something called transfer learning. The reason why they call it transfer learning is because when Google created it, they might have used pictures of boats, right? Well, we don't have pictures of boats. We have pictures of blueberry muffins or chihuahuas, right? So we can take their structure and how they and the logic of how they pulled apart the different pieces of the image and actually built it to make these predictions over here. We can actually take the structure of that and all the different weights that were on there from when we looked at the neural network, and we could take that as a starting point, and then we could build our own labels off of that. So that's what they mean when they say transfer learning. Okay, any questions about that? Clear as mud? Cool. All right, so now let's look at what the machine learning engineer would do. Well, the machine learning engineer would basically do something like this. I'm going to take the, I'm going to basically import the model, in this case, GoogleNet. I'm going to say model, create model, have it actually train the model on the things that we're looking at, and then that's it. So the machine learning engineer is figuring out how to actually use that model now to work with the data that they're specifically looking at. And I don't want to oversimplify that. So let's say that we trained our model on blueberry muffins or chihuahuas, but now we want to use it to determine if something is a sheepdog or a mop. This would be what the machine learning engineer does. They take the model that you built for the blueberry muffin or chihuahua, the structure of it. They then take that as a starting point for their new model that they're going to create. And then they would actually train that new model to actually determine whether it's a sheepdog or a mop. Okay, so I didn't want to oversimplify the machine learning engineer part because there is a lot more than just like 5 lines of code. But that's kind of how they take and actually apply transfer learning.
Hey, Brian, I have a question for you.
Sure.
So given the example that you have on the screen here, how many pictures of muffins versus chihuahuas versus sheepdog versus mops do I have to run through the algorithm to be able to depend on it and say it's accurate?
There's not necessarily a hard and fast rule, and they don't have to be equal in numbers. So if you look here, this is what 4 by 4 is 16. They don't have to be like, oh, we trained it on 16 images, now we have to use 16 images. It's not necessarily like that. And I think a lot of it is problem dependent. If let's say you're training on different types of documents, right? And let's say it's a standardized form. I might only need 10 or 20 samples of that form instead of 10,000 samples of that form, right? So a lot of it's going to depend on variability within the data type. And I think a lot of that is going to be project specific. Does that kind of make sense?
But,
yeah, so I don't want to give you the consultant answer of it depends, but it really does depend. And what you can kind of do is kind of like an educated guess and check. You could start with like, well, I think I can solve this with only 20 samples. Just give it the 20 samples, run it through the process, and then perform your metrics calculation on the training set, and then see how it performed.
Okay, thanks.
Yep. Okay, so one of the other things that a data scientist will handle is so I like to think of the data scientist too as doing like more complicated tasks than what the machine learning engineer would do. And one of the things they might do is, let's say that we have a data set where we're trying to maybe determine what type of document, maybe we're working with mortgage documents, but we're looking at bank statements. Bank statements are going to vary from bank to bank, right? And it'd be impossible for me to go to every single bank in the country and say, hey, can I get a sample of your monthly statements? Because they're going to laugh at you and say, no, get out of here. So one of the things that a data scientist will have to do is, and this kind of goes back to where they help out the machine learning engineer as well, is they might have to figure out how to break down that data. So they might perform clustering to say, okay, well, we have a large amount of data that we don't really have labels for, but we want to group things together. And now instead of having 10 million things to label, we only have 30 things to label. So that would be an example where you'd use clustering. The dimensionality reduction, like I alluded to earlier, that would be where we determine which features do we actually care about. And then to figure out that, you can use something called a principal component analysis. And that basically is what this graph is down below. It basically creates a graph of all the features, and then it determines which of those features are the most important and which ones you can drop off the model. So that if we're trying to determine bank statements, say, and balance is one of the data points we get back, it could say, well, don't put balance in there and your model would be a lot more accurate. So that would be an example of like the type of work that a data scientist would do, is they're trying to help break down the problem and figure out other strategies that might go in accordance with the model in order for the model to actually perform the way it should perform. Another thing they can do too is something called ensemble learning. And this would be, let's say, for example, we're doing a document classification for mortgages, and we're looking at bank statements. One of the things we can do is we can take our data in and we can run it through different models and then figure out how to combine the results for these and then make a prediction. So model 1 or model A might be we look at the text. Model B might be we look at the number of pages. And then model C would be we look at the, so text, pages, and visual. Maybe we look at the layout of it. So we could take the results of each of these things together and say, oh, well, that looks like the layout of a bank statement and it has the verbiage of a bank statement. Therefore, it's probably a bank statement. And then you could basically have an algorithm that combines those models together to actually make a prediction. So this is actually really powerful. And it's kind of one of the things of like a machine learning, of a data scientist has to do, is to figure out how many models do we create and how do we break those things down. Okay, so I'm just checking time. So let's talk a little bit about a couple of realities. So the first reality to all this is that most machine learning or data science projects do not exist on their own. They're not black boxes that just sit out here and do nothing, right? They're usually integrated into other systems, right? What good would it do to make predictions on something if you're not going to do something with that prediction? If you're not going to return it back to the customer, or if you're not going to use it for making decisions in your business processes or whatever, then it's basically useless, right? And most real-world machine learning projects will actually have more than one model. Just like I alluded to with that ensembling, you might have one that looks at that visually to look at the layout of the form, and you might have one that looks at the text of the form. And you might use those two in conjunction together to give you a lot more accurate results. So most real-world projects will actually employ more than one machine learning solution into the application. And this is a big one. So if there's bias in your data, machine learning will pick up on that and overly apply it everywhere. There's been several instances of that in the news where, let's say, for example, Amazon, we'll use Amazon's example, where they tried to build a system that would look at resumes that were uploaded and determine if that person was somebody they wanted to hire. Well, the problem is they had a disproportionate amount of data in there for men versus women. So what it would do is the machine learning algorithm picked up on that, and it determined that if you're a woman, then you're bad, so automatically reject you. And the reason why it did that is because they didn't take into account how to deal with gender differences for the way that people write, right? So men are more like strong-worded, and women are more embracing in general. And that might be like an oversimplification, but basically you have to take your data and you have to evaluate it for things like that. Because if it picks up on those, like, oh, you're too embracing, then we don't want you. And that could cause a lot of problems in your application. So it's one of the things you have to be careful of. And the biggest thing is the golden rule: thou must know thy data. You have to know and understand your data if you want to do anything useful with it. Okay, whoops. Sorry, I keep clicking it. Some of the other realities is there's what we care about as machine learning and data science people, and then there's what the client cares about. So we tend to care about things like recognition rate, precision, recall, F1 score, MAP if we're doing like computer vision analysis. Customer don't really care about that. This is one of the biggest realities that you have to understand if you start getting into this kind of work. What the customer cares about is how it impacts their business. So with my work with document classification for the mortgage industry, the thing that they cared about, so let's say that I had a 100-page document, right? And I got 98 of those 100 pages correct. 98% recognition rate, awesome. That's a really good solid model, right? Well, that's not what the business cares about. What the business cares about is I want indexers to not have to touch this file. So if that file is, and you only got 98% of those pages correctly, depending on which two you got wrong, that could actually mean 5 or 6 operations the person has to manually go do now. So what we had to do is we had to calculate and create a metric around how we would actually take a model, and based upon its recognition rate, we would actually calculate the end user impact, and then we would use that score to actually determine if the model was good. So even though you're at 100, even though you're at like a 98 or 99% recognition rate, that might still only equate to like a 50% error rate, or a goodness value, if you will. So that's one of the things you got to be careful of. And one of the other things too is that clients care about things such as like minimizing false positive rates. So I think we're probably over. Do I have a couple minutes left, or should I end it?
A couple minutes will be fine.
Okay, so let me give you an example about that from my work in autonomous vehicles. So there's something known as ADAS, which is assisted driver technologies for autonomous vehicles. And if, let's say that, for example, you are working at a company that does autonomous braking, right? So it's not fully autonomous. It's in a driver assisted technology where they want to look at, is somebody there, and then determine whether or not to apply the brakes. So false positives are really bad in those situations, because what that means is you said somebody's there when they actually weren't. And in that case, now you're braking the car unintentionally, or when you don't need to be. And that's gonna make situations that are very unsafe. It might lead to driver annoyance and things like that. So they care about minimizing those false positives. If you're talking about fully autonomous vehicles, where the car drives itself and doesn't have the driver there, then you care about false negatives. You would rather the car brake and not hit somebody because you said they were there, they weren't. So like your false negative says, like somebody was there but you didn't detect them, right? So like you obviously want to minimize that as much as possible. Otherwise, you're going to end up hitting somebody because you didn't see them. Okay, so like that's one of the things you got to keep in mind with this, is that a lot of companies will care about like different metrics than what we care about. Okay, so one more thing I want to mention. I want to give a huge thanks to our sponsors, especially Sam, for putting this all together in the global AI community, for allowing this to happen. And if you guys have any other questions, I'll stick around during the break. And that's my GitHub profile if you want to download the slides. And that's my Twitter handle if you have any other questions. So thank you, and I appreciate you guys for joining.
Thank you, Brian. Well done. Great presentation, and appreciate you taking the time to explain all the different terminology and share your experiences and some war stories and things to watch out for. So highly appreciate it.
Thank you. Thank you for having me. Appreciate it.